Welcome to our last lesson on oscilloscope fundamentals. If you made it this far, you deserve your engineering degree. Thanks for being patient with me. In this lesson, we are going to be talking about and demonstrating important oscilloscope specifications that you should be familiar with. Hi, my name is Johnny Hancock, Product Manager for Keysight's InfiniVision oscilloscopes. Oscilloscopes have lots of specifications, but there are a few important ones, including bandwidth, sample rate, vertical resolution, memory depth, and number of channels. But the most important oscilloscope specification is bandwidth. Bandwidth determines the fastest signals that can be accurately captured and measured. The front-end hardware on an oscilloscope is basically a low-pass filter. That means it can pass low frequencies, signals through to the analog to digital converters, which we'll be talking about a bit later, but it can't pass higher frequency signals to the ADC. It will begin to attenuate higher frequency components of the signal. The graphic on your screen now shows the typical frequency response of an oscilloscope. Attenuation, which is negative gain, is on the vertical axis, and frequency is on the horizontal axis. Perhaps you remember this type of plot from our lesson on Bode plots. The ideal gain of an oscilloscope is 0 dB, or an absolute gain of 1. If you input a 1 volt peak-to-peak signal, you want the scope to capture and measure 1 volt peak-to-peak, regardless of the frequency of the input signal. Unfortunately, we don't live in a perfect world, and scopes don't have infinite bandwidth. The -3 dB point is where oscilloscope bandwidth is specified. -3 dB is equivalent to an absolute gain of 0.7, which means that the input signal at the bandwidth frequency can be attenuated by as much as 30%, which is a significant amount of error. Let's do a bandwidth test on my oscilloscope. This oscilloscope, which is the one that we have been using for most of the experiments in this video series, has a specified bandwidth of 200 megahertz. Let's see if this scope meets its specified bandwidth. This is a 10 megahertz sine wave, 1 volt peak to peak. I've got some measurements up on screen here. First of all, there's a counter measurement, which I haven't talked about before. It has a 5-digit counter. You can see it reads 10.000 megahertz. And volts peak to peak says 1.01 volts, so pretty close to 1 volt. This signal is coming from it's a high frequency signal generator. It's similar to a function generator, except that it's focused on higher frequency signals, and it only generates sine waves, pure, almost perfect sine waves. This goes up to 4 gigahertz. We won't go that high. What we're going to do is somewhat of a manual test of bandwidth. I'm going to increase the frequency in increments of 10 megahertz until we see the amplitude begin to drop by approximately 3 dB, which is where the bandwidth is. That would be about a 30% drop in amplitude, which means the peak-to-peak voltage, when it drops to about 0.7 volts, that's the bandwidth. So let's start increasing the frequency. So there's 20 megahertz, 30, 40, 50, still measuring pretty close to 1 volt peak to peak. There's 100, there's 150 megahertz, still measuring pretty close to 1 volt peak to peak. There's 200 megahertz. Now I could change the time base if we want to see the cycles more clearly. And now it's down a little bit. This is the bandwidth. It's only down about 5%. So we have more than met the bandwidth. Now let's keep increasing. Now I can begin to see it decreasing. Now it's down about 10%. There's 220 megahertz. It's down almost 20%. 230 megahertz, a little over 20%. 240 megahertz, about 25%. and 250 megahertz, it's just slightly more than 30% down. So the bandwidth of this scope, even though it's specified at 200 megahertz, we're actually achieving probably about 245 megahertz. What happens if we keep increasing? I'll keep going up 10 megahertz at a time. You can see it's beginning to drop like a rock. So remember the low-pass filter curve, it rolls off and it drops like a rock. Now, one thing I want to make sure you're aware of, the output signal, the signal coming out of this BNC, is still 1 volt peak to peak, even though it says it's only about a 1/4 volt peak to peak right now. This is constant. What's happening is the analog hardware on the input of this oscilloscope can't handle the higher frequencies and it attenuates it. It can't pass them. So the test I just did to test the bandwidth, that's not the way we actually test bandwidth, manually creeping up and measuring it in the time domain. We actually use what's called a vector network analyzer that generates a frequency response plot like we showed in one of the earlier lessons on Bode plots. So anyway, how much bandwidth is needed? Well, it really depends on two things. What is the maximum frequency content of your signals and how much money do you have? The higher bandwidth scope, the higher it's going to cost. 200 megahertz bandwidth is sufficient for most university teaching labs. In fact, in many university labs I've been in, many of them use 50 megahertz bandwidth scopes. But once you get into industry, higher bandwidth may be required. My recommendation is I recommend that bandwidth should be 5 times the highest digital clock rate you intend to measure, especially for digital applications. And what this does is it allows your oscilloscope to accurately capture up to about the 5th harmonic. So remember when we talked about fast Fourier transforms, how digital signals, there's a fundamental and odd harmonics. Up to about the 5th harmonic is very important in order to capture the true nature of a digital pulse. So for example, let's assume your highest clock rate is 100 megahertz. I would recommend a 500 megahertz scope. If your highest clock rate is a gigahertz, then you better get at least a 5 gigahertz bandwidth scope. So what other specifications are important? How about sample rate? So let's do a test and see if this oscilloscope has sufficient sample rate to capture its full bandwidth, which is 200 megahertz. So my generator is currently setting at 330 megahertz. I'm going to roll it back down to 200 megahertz. So there's a 200 megahertz sine wave. Let's do a single shot acquisition. There you can see it captured the sine wave. Now this scope samples at 2 gigasamples per second. That's the maximum sample rate. So you would think at 2 gigasamples per second, sampling a 200 megahertz sine wave, you would just see 10 points. We're seeing a lot more than 10 points here. The reason is this scope automatically runs a sine x over x reconstruction filter that creates a continuous waveform. Now, you may also be familiar with Nyquist, who says all you need for sampling is 2 over the highest frequency. But this is not a perfect world. The highest frequency is not the same as bandwidth. Now, there's a white paper I wrote, I'll reference at the end of this lesson, that you can download that does a deep dive into Nyquist and why it doesn't quite apply to an oscilloscope. But my recommendation is that the sample rate for lower bandwidth scopes of 1 gigahertz bandwidth and lower, the sample rate should be 4 to 5 times higher than the bandwidth. So we have 10 times higher. So we're above that 4 to 5 times criteria. Now, higher bandwidth scopes, multi-gigahertz scopes, they can come a little closer to the Nyquist, and they can do about 2.5 times the bandwidth for this sample rate. And again, that's explained in the application note. Now, there's one more important specification we want to demo, and that's vertical resolution. Scopes use ADCs, or analog to digital converters, to convert an analog input into discrete levels. Most entry-level scopes like this one have 8-bit A to D converters. And so 8 bits means 2 to the power of 8. They resolve them into 256 discrete levels over approximately 10 divisions, which is approximately the screen height here. Can you see those levels? Currently, it looks like a continuous waveform. If I do a single shot acquisition, we can see things jumping. If you look real close, you can see things jumping up and down a little bit. But the only way to really see the discrete levels of even an 8-bit converter is, now that we have it stored, I'm going to zoom in on the stored waveform. And there, it looks like stair steps. You can see the discrete levels. Now, I originally captured this at 200 millivolts per division. The dynamic range of the analog to digital converter from the low end to the high end is 2 volts, 10 divisions. And you divide that by 256, it means each discrete level should be 8 millivolts apart. I'm currently at 10 millivolts per division, and I can see each of these stair-step levels is about 8 millivolts. Now, that's not the minimum resolution of the scope. If I had started from, say, 5 millivolts per division, then I'd have a different dynamic range, in which case I'd have 200 microvolts of resolution. So, would it be much better with 8 bits or 10 bits? Not really. Scopes have a small amount of noise inherent in them. We call it baseline noise, and that's typically more than 8 bits. And so getting more than 8 bits, especially in the university environment, all you're going to be doing is digitizing noise with more detail and not digitizing your signal. So 8 or 9 bits isn't going to do much better for this application in the university environment. So we just talked about and demonstrated bandwidth, sample rate, and vertical resolution, or ADC bits. But there are a few other specifications I would like to briefly cover. Memory depth, or maximum acquisition memory, can sometimes be important. The more memory a scope has, the longer time span it can capture at its maximum sample rate. This scope has 2 million points of acquisition memory, which is probably more than enough for your experiments as an undergraduate student. Some higher performance scopes, as well as higher price scopes, have gigabytes of acquisition memory. The last specification we're going to talk about is number of input channels. When I was studying engineering over 40 years ago, 2-channel scopes were all that were available. Today, 4-channel scopes are very popular, which is what I have been using for all of my demonstrations in this video series. But for most of your experiments, 2 channels may be enough. I should also mention there's another class of oscilloscope called a mixed signal oscilloscope, or MSO, that adds 8 to 16 digital channels of acquisition. That means that these additional 8 to 16 channels can only show if the signal is above or below a threshold setting. This graphic on your screen now shows an oscilloscope's display with both analog channels and digital channels turned on. The waveforms at the bottom of the screen are from the digital inputs. MSOs can be very handy if 4 analog channels aren't enough. One more thing to mention, but it's not an oscilloscope specification. How easy is the scope to use? Is the front panel GUI intuitive? Is it responsive? Unfortunately, you can't easily rate the usability of an oscilloscope and put a number on it. But usability is very important, and every scope vendor claims that their scopes are the easiest to use. This is something that you'll have to judge for yourself. Well, that's it for this video series on the fundamentals of using oscilloscopes. it has been my pleasure to be your instructor for these lessons on oscilloscopes. I have one last piece of advice for you. Learn how to use your oscilloscope. If your oscilloscope can become second nature to you, this will allow you to focus more of your attention on learning about the electronic concepts and theory rather than spending time fumbling with the oscilloscope, which is what a lot of students end up doing. If you want to learn more about bandwidth and sample rate, which were covered at a fairly high level in this lesson, I've written papers on these topics in more detail that you can download at the URL listed on your screen. Sorry if I didn't get to your university in this video series. My manager would only approve of me purchasing a limited number of university shirts. So, go Longhorns, go Gators, go Sooners, go Dirtbags, go Aztecs, go Ducks, go Cowboys, go Rams, go Rattlers, go Crimson Tide, go Bobcats.